Consider a 0.25 meter long vertical plate with a 10 centimeter width that is at 70 Celsius. The plate is suspended in air that is at 25 Celsius. Determine the rate of heat loss from the vertical plate as a result of natural convection. So I have a little drawing that I did of the situation here. We have our vertical plate. I've suspended it in these green chains here. And it has 10 centimeters width, and it has 25 centimeters or 0.25 meters height. Now, note that they're only giving two dimensions because one of the dimensions is negligible, right? It's very small, so that we're not considering, like on the previous problem, we're not considering this side or this top part here either, okay? So those guys are negligible. You can disconsider them. We can actually do, if you want, we could go ahead and do this and make it even thinner, like that. Okay, so that could be our new vertical plate. Okay, so we don't need this chain anymore, or this chain. Okay, so it's a very, very thin plate, so that we're only considering two sides of it. Oops, I didn't want to do that. What I wanted to do was this, get it out of there so it's not overwhelming. Well, since we know the air plate is hotter than the ambient temperature, we know Q is indeed going out, so the plate will indeed lose heat to the environment. Now, this is a natural convection case. Nothing said about anything enclosing. It's not a cavity or anything like that. So that means that this is a non-enclosed situation, non-enclosed. So this is a non-enclosed natural convection situation or free convection situation. Okay, so if that's the case, then our go-to equation is, or correlation I should say, is Prandtl times Grashof, which is Rayleigh, to the M, right? M as in mechas. So what do we need to do to be able to solve this? Well, we need to find what these guys are, right? So the Prandtl I'll find by looking at table. This says air, is it? Air. This is air. So I'll be looking at table A5 to grab the properties of air. The Grashof I'll be calculating by inputting gravity, beta, characteristic length, density, and viscosity. And then after I have those two guys, then I can find out what are these guys here from our table. Okay, so this is the table for isothermals with constant, non-enclosed space, and I have a vertical plate, so I have this situation here. So in order to determine the coefficients that I'm looking for, I'll need to find out what is Rayleigh number, right? And Rayleigh, just as a reminder, Rayleigh is just Prandtl times Grashof. Okay, so how can we do that? Let's start by finding properties, and I want properties at T film, and I know T film is 25 plus 70 divided by 2. This is air, so properties are given in Kelvin, so I want to sum up 273 to that. So T film is 320.5, so 320.5 Kelvin. Okay, so what I'll do is I'll grab properties for this. And since we had some people claiming that they wanted to use the density as opposed to the kinematic viscosity, let's go ahead and grab all these properties. So density, nothing said about pressure, so we can assume 1 atmosphere, so this is just as good for density. What else? I'll need the viscosity at 320. I got that to be 1.94. This is all from table A5, by the way, which I think I have here as well. Yeah, so table A5, and I'm interested in 320. So between these two guys, and I had to interpolate to grab these values, right? So the density is going to be between these two guys. The viscosity, I'm also needing this guy, conductivity, and I'll need Prandtl, so I'll need this guy too. Okay, so 1.94 times 10 to the minus 5 kilograms meters second. Conductivity at 320, 0.7035 watts meters Kelvin. Prandtl at 320 is oh, never mind. This was Prandtl. So no units there. And then K is 0.02779. My bad. Okay, so now what are we looking for? Remember that we need Prandtl and Grashof. Prandtl is already here, done. The other thing we need is Grashof, so let's find Grashof. Grashof is density, gravity, beta, x to the third, delta t divided by viscosity squared. We are missing beta here from these things, and we know beta, if it's an ideal gas, and we can consider air to be an ideal gas, will be 1 over T, as long as T is in Kelvin, so this T film, right? So in this case, our T film is 320.5. So that means that my Grashof will be 1.1038 for density, 9.81 for gravity. Beta will be 1 over 320.5. Characteristic length of a plate is the length of the plate, right? So in this case, the height of the plate, 25 centimeters, so 0.25 meters, so 0.25 meters to the third, and delta T, we had the plate at 70 and T infinity as 25. So there you go, delta T. And we're dividing all that. Let's see if I can make a straight line. Yeah, that was pretty good. 1.94 times 10 to the minus 5, and I'm squaring that. So Grashof, this whole thing becomes 6.97 times 10 to the 7th. Great. So if I have these two values, Prandtl and Grashof, then Rayleigh number becomes trivial. It's just a multiplication of the two. And I get 4.9 times 10 to the 7th. Okay, so what do we need to do now? We need to go back to our table with this number here in mind, with this order of magnitude, I should say, and figure out what is the C and the M in our Nusselt correlation. So let's go back to our table. There you go. So we're looking for a correlation for these guys here, right? And we have 10 to the 7th, and 10 to the 7th will fall over here, right? So that means that our Nusselt will be 0.59, our M will be 1/4. So now I can find Nusselt, which is 0.59 times Rayleigh, 4.9 times 10 to the 7th to the 1/4, to the power of the 1/4, and that's it, right? That's it. And this gives me 49.4 approximately. 49.4 for Nusselt number. Great. Now I have Nusselt. With Nusselt, it's pretty easy to find Q, right? Because I'm going to use Nusselt to find H. With H, I'm going to find Q. So let's keep digging. We know Nusselt equals convective coefficient, characteristic length divided by the conductivity. Characteristic length of the plate is L, or in our case here it's the height, right? So therefore, therefore H will be 49.4 times K divided by 0.25. K is that number that I got wrong before. Here it is. This turns out to be 5.49. And with this number, we can move to find Q, right? Which is what we're looking for from the start. We're looking for Q, and we know Q is the H times the area times the delta T. So in this case here, 5.49. Area is, what's the area of the plate? 0.25 times, what's the other dimension? 10 centimeters. 0.1. And $70 minus 25. completely lost track of what I was doing. So this is watts per meter squared Kelvin. I'll multiply this by meters and by meters again by Kelvin. So I'll have the answer in watts. Boom, 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 boom. So answer in watts. So one side of the plate will give me 6.17 watts. Right? So let's see what the question is asking. Determine the heat loss from the vertical plate as a result of natural convection. So it wants the whole thing, and the whole thing has two sides, right? So there's two ways to think of it. We can think of it as this Q here that we drew before being 6.17. Therefore, if we have two sides, we're going to have 2 times that Q, which is 12.3. Or you can think of the area being double over what we just calculated, right? Because we have one area here, and we also had the same area on the other side. So when we're calculating the area here, where is it? So when I calculate my area here, instead of having it as 25 times 0.1, I would have it, so let's do total. I would have it as 5.49 times 0.25, 0.1 times 2, because I have 2 of these surfaces. And then that is times 17 minus 22. Right? So either way, we'll have 12.3 watts. Okay, so if we, depending on what you guys did, I might give you full marks if you justified. But my interpretation, the total energy that is being lost to the environment under these conditions is 12.3 watts because we have 2 sides to this plate. If you have questions, send me an email.